Okay, students, let's talk about reaction stoichiometry. So what we want to do is look at a problem. Let's look at some example problems so we can figure out how to um, do reaction stoichiometry. Um, so we have ethanol, which is added to gasoline to produce gasohol. And we typically use this for fuel and automobile engines. And they want us to calculate the number of grams, so number of grams of oxygen that's required to completely combust 421 grams of ethanol. So they give us grams of ethanol and they want to know how many grams, given this many grams of ethanol, 421 grams, how many grams of oxygen will we need to combust that many grams of ethanol. So the first thing I tell students whenever you're confronted with a reaction stoichiometry problem is to first make sure the chemical equation is balanced. So let's see, we have 2 carbons here, we have 6 hydrogens, and we have, let me see here, that's 7 oxygens on this side. Okay, so remember this arrow is like an equal sign, so we have to have the same number of atoms on both sides of the chemical equation. So we got 2 carbons here, we have 3 times 2, that's 6 hydrogens, and then I have 2 times 2, so that's 4 oxygens here, and then I have 3 times 1, that's 3 oxygens here, so that gives me a total of 7 oxygens. Okay, so I'm balanced. Remember, you always just want to check just to make sure, even though you may see stoichiometric coefficients here in front of your substances, just double check just to make sure that you have a balanced chemical equation. Okay, so now what we need to consider is how we're going to go from grams of ethanol to grams of diatomic oxygen. All right, so what we need to consider doing here is going from, let's just get us a little roadmap here. We'll say, okay, we're gonna go from grams of ethanol, and what we need to do is get in moles of ethanol. Why are we getting in moles of ethanol? Because what these two have in common is their mole ratios. See, it's a 1 to 3 mole ratio between ethanol and oxygen. So if I can get in moles of ethanol, that will allow me to use the mole ratio to get in moles. That will give me number of moles of diatomic oxygen. And then once I'm in moles of diatomic oxygen, guess what, guys? I can use the molar mass to get what? Number of grams of diatomic oxygen. So this is the roadmap. This is our roadmap. This will lead us to grams of diatomic oxygen. So, all right, so we can take it a step-by-step process, and then I'll show you how we can do it in just one big step. So let's take the step-by-step process. The first step is we're going to say we're going to convert the grams of ethanol to moles of ethanol. So I'm going to say number of moles of ethanol. Well, given 421 grams of ethanol, right? If I use the molar mass as a conversion factor, check this out, guys. We got 2 carbons, so that's 24 grams, 6 hydrogens, so that's 6 grams, and then 1 oxygen, that's 16 grams, so that gives me a total of 46 grams equaling to 1 mole for that particular substance. That's the molar mass of ethanol. Okay, so I want to get rid of grams, so I'm going to put 46 grams of ethanol at the bottom. And I'm going to put 1 mole because that's what I want, moles of ethanol. Given the grams of ethanol, I want moles of ethanol. All right. And so I multiply 421 grams of ethanol times 1 mole of ethanol divided by 46 grams of ethanol. And that's going to give me 9.15 moles of ethanol. Let me rewrite this here. All right. So C2H5OH. All right. So now that I'm in moles of ethanol, guess what? Now I can use this mole ratio, this 1 to 3 mole ratio, to get in moles of diatomic oxygen. So in step 2, that's what I'm going to do. Number of moles of diatomic oxygen is simply going to equal to 9.15 moles of ethanol. And I'm going to use the mole ratio here, this 1 to 3 mole ratio, as a conversion factor. So 3 moles of diatomic oxygen will go up top. I get this 3 from the coefficient here, okay? It's a 1 to 3 mole ratio here between ethanol and diatomic oxygen. So I want to get rid of moles of ethanol, so I'll put 1 mole of ethanol at the bottom so that moles of ethanol cancel. Like grams of ethanol canceled here and left me with moles of ethanol. So now I'm in moles of ethanol, so I multiply the moles of ethanol times the mole ratio to get in moles of diatomic oxygen. And so that's going to give me 27.45 moles of diatomic oxygen. Now check this out. Remember, if I'm in moles of a substance, to get in grams of that substance, I just multiply by that substance molar mass, right? So this is 27.5 moles of diatomic oxygen, and I'm just going to multiply by the molar mass of diatomic oxygen. Well, the molar mass of diatomic oxygen, I have 2 oxygens, so that's 2 times 16. So molar mass is expressed in grams, equaling to 1 mole of that substance, right? So 2 times 16 is 32. Well, that's 32 grams that is going to equal to 1 mole of diatomic oxygen, okay? So I'll put 32 grams of diatomic oxygen up top, and I'll put 1 mole. So for 1 mole of diatomic oxygen, I have 32 grams of diatomic oxygen. So that the moles of diatomic oxygen cancels, now I'm left with grams of diatomic oxygen. And so when I carry this calculation out, I get 878 grams of diatomic oxygen. And so this is the number of grams of diatomic oxygen that is required to react with 421 grams of ethanol. All right. Now, if I was to carry this calculation out in one big, gigantic calculation, I would say, okay, number of grams of diatomic oxygen is simply equal to, start out with 421 grams of ethanol. All right. And I'm going to multiply times 1 over ethanol's molar mass, so that'll be just moles of ethanol per number of grams. of ethanol, which is 46 grams. So for 46 grams of ethanol, I have 1 mole of ethanol. All right. Now I want to get in moles of diatomic oxygen, so I use the mole ratio. So it's 3 moles here. Sorry about this. It's a little tight here, guys, and I apologize for that. All right. So for 3 moles of diatomic oxygen, I have 1 mole of ethanol. We get that from the balanced chemical equation. And this is why we want to make sure that our chemical equation is balanced. I'm going to try to tighten this up a little bit, okay, so that I can have some room. So this is grams of diatomic oxygen. All right. So now I'm going to take the moles of diatomic oxygen and multiply times the molar mass of diatomic oxygen, which is 32 grams of diatomic oxygen is equal to 1 mole of diatomic oxygen. So what we see here is that our units, yes, a mole is a unit. Of course, you know a gram is a unit. Our units cancel, leaving us with our desired unit, and that is grams of diatomic oxygen. And so again, this is equal to 778 grams of diatomic oxygen. All right. So we can break it up into steps, into 3 distinct steps here if we're going from grams of one substance to grams of the other substance, or we can do it in one big step like we did here at the bottom. All right, guys. So this is reaction stoichiometry, and this is how we approach it. The first step, though, in this is making sure that your chemical equation is balanced. Even though it may look balanced, double check just to make sure it doesn't hurt. All right. And then once we do that, we can then go about doing the calculation. So if we're in grams of a substance, then we get in moles of that substance. And then we use the mole ratio to get in moles of the other substance. And then we use the molar mass of that substance multiplied times the moles of that substance to get the grams of that substance. Okay. So we'll look at another problem similar to this, and then we'll continue with our discussion of reaction stoichiometry, but we will hone it down to calculating what we call theoretical yield. Okay, guys, this is a continuation of reaction stoichiometry, another problem we're going to work through. In photosynthesis, green plants convert carbon dioxide and H2O to glucose. How many grams of carbon dioxide are required to produce 5.1 grams of glucose? All right, so what we have here, we want to know if we're going to produce 5.1 grams of glucose. This is glucose, by the way, C6H12O6. Then we want to know how many grams of CO2 am I going to need to produce this 5 grams of glucose. So we can work backwards here. Again, you want to check to make sure your chemical equation is balanced, even though you may see these coefficients. Again, it doesn't hurt to just check and make sure. So we have 6 carbons here. We have 12 hydrogens here. 6 times 2 is 12. And then we have 6 times 2 is 12 oxygens here. 6 times 1 is 6. So 6 plus 12 is 18. So we have 18 oxygens on this side. Again, think of this arrow as an equal sign because I have to have the same number of atoms on both sides of the chemical equation. Okay, so we have 6 carbons here, we have 12 hydrogens here, And then we have 6 oxygens here, and then 6 times 2 is 12, so 12 plus 6 gives us 18 oxygens here. So I'm balanced, okay? So let me draw a little arrow, a little line through here. Now remember, the reason why we have to balance the chemical equation is because of the law of conservation of matter, which says matter can neither be created nor destroyed. We can only convert from one form of matter to another. So we have to have the same number of atoms, even in a chemical reaction, on both sides of the chemical equation. Okay, so recall in the previous problem where we first, if we were in grams of this, right, grams of glucose in this case, what do we want to do? We want to get in moles. We want to get in moles of glucose, right? So we'll use the molar mass as a conversion factor that'll allow us to go from grams of glucose to moles. So we need to think multiplying by 1 over the molar mass will just be moles per grams of that substance. And then once we're in moles of glucose, then we want to utilize the mole ratio to get in moles of carbon dioxide. And then once we're in moles of carbon dioxide, we can get in grams of carbon dioxide. All right, so here we're going to utilize the mole ratio to go from moles of glucose to moles of carbon dioxide. And really this is why we have to make sure the chemical equation is balanced, because we're going to utilize the mole ratio. And you only utilize the mole ratio when you are converting from moles of one substance to moles of the other. Do not use the mole ratio or the coefficient to calculate molar mass. Okay, I repeat, do not use the stoichiometric coefficients to calculate molar mass. Do not do that. You're only going to use the coefficients when you're going from moles of one substance to moles of the other substance. That's it. Okay? So once I'm in moles of carbon dioxide, then I will utilize the molar mass of carbon dioxide to get in moles, to get in grams of carbon dioxide. So let's work this problem out, guys. All right. So I'm gonna say I'm just gonna do one big step here. So number of grams of CO2. Number of grams of CO2 is going to equal to, well, we start with our 5.1 grams of glucose here. Okay. And we need to calculate the molar mass of glucose. Well, if you calculate the molar mass, right, we got six carbons, so that's 6 times 12. We got 12 hydrogens, and we'll go grams since we're calculating molar mass. So each hydrogen the molar mass of each hydrogen is 1 gram. And we got 6 oxygens, so that's 6 times 16, so we get 72 grams here, we get 12 grams here, and we get 96 grams here. So that gives us a total of 180 grams for glucose, which is also equal to what? 1 mole of glucose. All right, so I can take that. I'm trying to get in moles of glucose, so I use this as a conversion factor. 1 mole of glucose is equal to 180 grams of glucose. So I'm going to use that molar mass as a conversion factor to go from grams of glucose to moles of glucose. All right. So here we go. This is how it sets up, guys. All right. So that grams of glucose cancels. Remember, when the units are diagonal to one another, you cancel them out. All right, so now I'm in moles of glucose. What's my next step? Well, I want to get in what? Moles of CO2. Well, how am I going to do that? I'm going to utilize the mole ratio. So for 1 mole of glucose, I have 6 moles of carbon dioxide. So I'm going to write 6 moles of carbon dioxide up top. And I will write 1 mole of glucose on the bottom. And watch this. Moles of glucose. Remember, mole is a unit, amount of substance. It's a SI unit for amount of substance. So we cancel the moles of glucose. Now I'm in moles of CO2. Now, to get in grams of CO2, I need to calculate the molar mass of CO2. Well, the molar mass of CO2 is going to equal to, well, I have 1 carbon, so its molar mass is 12 grams, and I have 2 oxygens, so the molar mass of each oxygen is 16 grams, so that's 12 grams plus 32 grams, so that gives me a total of 44 grams of carbon dioxide, which is equal to what? 1 mole. 1 mole of carbon dioxide. So for 44 grams of carbon dioxide, that is equal to 1 mole of carbon dioxide. So moles of carbon dioxide cancels, thus leaving me with grams of carbon dioxide. And when we carry this calculation out, I get 7.47 grams of carbon dioxide. So there we go. All right. So I guess if we want to get down 2 sig figs, we could report this as 7.5 grams of carbon dioxide. Let's go with that. 2 sig figs, because we have 2 sig figs here. So we'll go with 2 sig figs here. So we'll report this to 2 sig figs. Okay. All right. So this is how we do it, guys. This is how we do reaction stoichiometry. You start out with number of grams of a substance. Then guess what? 1 over, you multiply the number of grams of that substance by 1 over its molar mass, which just means it's the 1 mole of the substance divided by the grams in 1 mole of that substance. Okay, so you get rid of grams that way. And then you multiply by the mole ratio. And then once you're in moles of the other substance, you simply multiply by the molar mass of the other substance to get in grams. Now, something I should tell you. If you're already in moles of a substance and you got to convert to grams of another substance, you skip this step, right? You just go from moles of that substance to the mole ratio, and then once you get in moles of the other substance, multiply it times its molar mass to get the grams of the other substance, okay? But if you're in grams, you first have to get in moles of the substance, then use the mole ratio to get in moles of the other substance, and then once you're in moles of the other substance, multiply times its molar mass to get the grams of the other substance. Okay, so I hope this video was helpful. Again, we will look at calculating theoretical yield as well as percent yield in another video. So as always, happy studies.